Hello, everyone, and greetings from Qatar. I would like to take this opportunity to hope all you are okay and staying safe, especially during this unusual time. Today, in this presentation, I am going to talk about electric vehicle integration in hot climates in terms of the power system perspective. And I will provide some outcomes from our project in Qatar Environment and Energy Research Institute. Before starting the presentation, I also would like to acknowledge that this project has been funded by Qatar National Research Fund. Let me start with the agenda of the presentation. First, we will start with the introduction, including the history of electric vehicles, some important technology developments, and the main components of electric vehicle technologies. After that, I will give brief information about Qatar, including load profile, etc. Then I will present research outcomes that investigate peak load impact on Qatar power system. After that, I will explain the concept of smart charging and along with one case study. And finally, conclusion will be presented. Here, I would like to talk about the early history of electric vehicles, as you can see in this slide. Electric vehicles first appeared in the middle 19th century. An electric vehicle had the vehicular land speed record until around 1900, we can say. And as you know, the high cost and the low top speeds and short range of battery electric vehicles, if you compare with the 20th century internal combustion engine vehicles, led to a worldwide decline in their use as private motor vehicles. However, electric vehicles have continued to be used in the form of loading and freight equipment and even in the public transportation, especially in rail vehicles. I'm not sure whether you heard about this interesting race was held almost 50 years ago. In 1968, the Great Transcontinental Electric Car Race was held between student groups at Caltech and MIT. The Caltech team converted a 1958 Volkswagen microbus powered by lead cobalt batteries, and the MIT team converted a 1968 Chevrolet Corvair powered by nickel cadmium batteries. And the MIT team raced from Boston, Cambridge to Pasadena, California, while the Caltech team raced the opposite direction. And a network of 54 charging locations was set up along the around 3,300 miles route, spaced 21 to 95 miles apart. You can see there were 54 charging stations, and it happened almost 50 years ago, and it was quite interesting. And you can see the technology they are charging the batteries through the transformers, etc. And you can get more information about this link. Here I would like to talk about a little bit about the vehicle electrification. And as you know, here you can see the conventional electric vehicles, which has the fossil fuel. It can be gasoline or diesel. And we have internal combustion engine. And of course, we have the transmission system. You know, most of the automobile companies are working on new technologies to improve the efficiency of this technology. I mean, the conventional technology to reduce the greenhouse gases and mainly caused by fossil-based fuels. First of all, they introduced the let's say, vehicles or hybrid electric vehicles. This kind of electric vehicles powered by both gasoline and the battery, or we can say electricity. The electric energy is generated by the car's own braking system to recharge the battery. And the two motors are, I mean, the electric motor and the engine are controlled by an internal computer or internal microprocessor unit that ensures the best economy for driving conditions. Later, the companies introduce battery electric vehicle, or we can say only electric vehicle. These are fully electric vehicles with rechargeable batteries and no gasoline engine, as you can see here. And battery electric vehicles store electric on board with high capacity battery pack. Their battery power is used to run the electric motor and all other onboard electronics. And this one is the newest technology in the market. For example, we can say Tesla Model 3 or Chevrolet Bolt or Nissan Leaf. And for the hybrid, we can say the most maybe popular or most used one is the Toyota Prius and also Honda Civic Hybrid. And as we told, unlike the electric vehicles or battery electric vehicles, hybrid electric vehicles contain the electric motor and internal combustion engine that run with gasoline or diesel. And here you can see in this table, we can have different degrees of hybridization. If the vehicle is, let's say, micro hybrid, if it is automatically stops and starts the engine in stop and go traffic. It is very basic technology, and we are calling this one as a micro hybrid. And if the car is used regenerative braking and operates above 60 volts or uses an electric motor to assist the combustion engine, we can call this kind of technology mild hybrid. And full hybrid, if it can drive at times using only the electric motor, maybe let's say 30 kilometers or 50 kilometers with the battery, it can drive at times using only the electric motors. It's full hybrid. And we also have plug-in hybrid. So this plug-in hybrid can be recharged battery from a wall outlet from extended all electric range. And here I would like to talk about the well-to-wheels efficiency. One common argument against electrifying the car is that all it really does is move the engine from one place to another, from your car to power plants, as you can see here, all the way. There is advantage to moving that exhaust away from people, because you can see there is no exhaust here. But overall, we can say it's argued the efficiency is pretty limited. And if we are going to compare the electrics to conventional internal combustion engine cars, we need to get our measurements right. With conventional fuel cycles, we often want to know about two primary numbers: the tanked wheel efficiency, which tells you how efficiently your engine turns fuel into movement, and of course the well to wheel efficiency, which adds the energy it took to get that fuel to your gas tank. And let's look at from here, for example, for the electric vehicles, from wheel to, let's say, the charging locations, the efficiency will be around 31, because the generation efficiency will be around 33, and transmission efficiency will be 94. Of course, these numbers are roughly. And plug the wheels efficiency is around 60, let's say 76%. And finally, we will get around 23% of efficiency. On the other hand, if you look at the conventional way, and refining is the efficiency is around 82%, and transmission 98%, and we can get 80% efficiency from, let's say, well to petrol station. But on the other hand, if we look at the efficiency of the pump to wheels is around only 16%. So the overall efficiency will be 13%. So again, this numbers is just roughly, and maybe you can find more recent numbers. You can just Google and Google it, and you can find more efficiency. And you can see, even with these numbers, we can say that the electric vehicles efficiency is higher than the conventional cars. And now I would like to give brief information about charging technologies, what we are using nowadays. And the charging technologies can be divided into three main streams, or can be broadly classified into two types: AC charging system and DC charging systems. AC level 1 charging, here you can see AC level 1 chargers are in the first category, and this kind of chargers for residential use only. It takes about let's say around 17 hours to charge an electric vehicle that has around 24 kilowatt hour battery. On the other hand, here you can see the AC level 2 chargers are in the second category, and these chargers can either be installed in the homes or can be used in public charging stations. And this kind of charger can charge and the same electric vehicles around in 8 hours. And the last category you can see here, DC fast chargers, and are in the third category, and these chargers are meant for public charging stations alone. They need three-phase AC input from the grid and consume more than 50 kilowatt power. And these chargers can charge the same electric vehicles in around maybe less than 30 minutes. Of course, the charge time you can see is only state of the charge will be 80%. In this slide, you can see the overall structure of the AC, and I will also show you the DC charging stations. A typical AC charging station is shown in this picture. As we can see, the AC from grid is supplied directly to OBC, onboard charger, through the charging system, electric vehicle supply equipment. The OBC then converts it to the DC, because here we have the AC, then onboard charger converts it into the DC and charge the battery. And here we have the pilot wire, and this pilot wire is used to sense the type of charger connected to electric vehicles. For example, it can be level 1 or level 2 or different, let's say, charging level, and send the required input current for the onboard charger. And here we can see the typical DC charging system. And as you can see, electric vehicle supply equipment, or let's say, let's call it charging stations, provides DC directly to battery pack bypassing the OBC. You can see it's bypassing the OBC, and it provides DC power to battery pack directly. And here the electric vehicle supply equipment is arranged in stacks to provide high current, since a single stack will not be able to provide high current due to power usage limitation. And the advantage of this type of charger is its fast charging time, while the disadvantage is it has complex engineering and of course the cost. And another electric vehicle charging technology here is inductive charging, also known as wireless charging or cordless charging. Is a type of wireless power transfer. It uses electromagnetic induction to provide electricity to charge the electric vehicle battery. Much like placing your smartphone on a charging pad each night instead of plug it in. And wireless car charging will fill your vehicle's battery when you park over a charger, as you can see in this figure. Just park your car over the charging conductor, so it will start to charge your battery automatically. Of course, this technology is not mature, and many things need to do in order to make this technology mature. And before moving forward, I would like to emphasize here. Actually, I believe that the fast electric vehicles chargers with renewable energies and stationary energy storage systems would help the grid operators to manage the demands. Because especially for fast chargers, since they require higher power from the grid, integration of renewable energy along with the stationary energy storage system may help the grid to manage the high demand. Of course, in addition, this kind of charging stations helps to reduce CO2 emission. Significantly, since its primary source is renewable energy. I would like to show you one example of renewable energy along with the stationary energy storage system EV charging station in Qatar. It recently opened, and you can see the PV installed on the parking area, and the total power is 72 kilowatt peak, and it also has a stationary electric storage system based on the lithium-ion battery, and you can see 170 kilowatt hour. And the electric vehicle charger, which is here, is level 3 charging, and the maximum power output is 100 kilowatts. You can get more information from this source. Now, we all see the market reports, and these reports show that penetration level of the electric vehicles has been increasing drastically in the recent past. This will bring consequences to the power grids, mainly in terms of peak load management and power quality issues, as you can see in the slides. For that reason, it is essential to evaluate potential grid impacts due to electric vehicle integration to ensure consistent grid operation. It is important to know when we charge peak time or off-peak time, or where we can charge workplace, home, or public charging places, or how we are going to charge fast, slow, and etc. Now you can see in this slide, I would like to share some results. As we know, peak load is a key system parameter. How much generating capacity will be needed when demand is highest? And planning around peak load helps ensure that the generation, transmission, and distribution capacity of an electricity system can meet consumer needs without risking any outages. The potential impact of electric vehicle charging on peak load in the focus regions were considered in this study, you can see, and more information you can find from this source. And in this study, they considered different kind of charging stations, charging technologies, for example, level 1, level 2, DC fast charging, 20 kilowatt and 40 kilowatt as well. And of course, the penetration level. They assumed then 1%, 3%, 5%, and 7% of penetration level. And it compares each country's maximum potential peak load impact from electric vehicle charging. Of course, it's based on various percentage of the households with an electric vehicles. And as you can see, the maximum potential impacts each shown as a percentage of the system baseline peak load, and assume that all electric vehicles are connected to grid when system demand reach its annual peak. Based on this analysis, we can say US and European electric grids are better equipped to handle electric vehicle charging loads compared to the electric grids in China. And peak grid impact can be mitigated with low capacity charging. If you look at here, for example, if we use only level 1 and level 2 charging stations, the load impact will be lower. On the other hand, if we try to use the DC fast charger, you can see the impacts on the grid will be higher. Here, Qatars Profile is given to better understand the impact of electric vehicle on the local grid. There is some important information about Qatar, as you can see here. Total population is around 2.7 million, and 85% are expats. And it is the energy capital of the world and the largest LNG supplier. And the electricity is generated from natural gas. And the important thing is that highest electricity consumption per capita. And here I would like to share with you some system max and minimum demand. You can see here system maximum and minimum demand load curve in 2017. The system maximum reached around 8 gigawatts on 14th August, and the system minimum is around 2.6 gigawatts on 25th February. It is clear that the consumption in summer almost 3 times higher than the consumption in winter due to the AC loads because of the the harsh environments. And I would like to also share another interesting results. Daily AC versus non-AC load energy consumption data here on the left hand side, and the red dots you can see here are AC consumption, while the blue dots are the non-AC consumption. And this is only from one house. As you can see here, especially during the summertime, okay, AC load is dominant and its consumption is around 75 to 80% of the overall consumption. To sum up, peak load is a key system parameter in Qatar because of the AC load, especially during the summer. How much generating capacity will be needed and when demand is highest. Even though peak loads tend to align with specific seasonal, electric systems must be able to deliver the maximum load at all times. It must. As I mentioned before, a fleet of electric vehicles may increase peak loads if charging aligns with maximum demand for other users. Okay, since we have the highest demand here, if we are going to charge our EV fleets at the same time, it will create some problem for the grid perspective. Now here I would like to present some interesting results of our initial study that investigate the potential peak load impact from electric vehicle charging in Qatar. This study compares the maximum potential peak load impacts from EV charging based on different penetration levels. You can see here. A stochastic simulation model is developed to assess the impacts of electric vehicle charging on power generation. For electric vehicle sales statistic, 5 scenarios are considered. As you can see here, the first 4 scenarios assume new electric vehicle registration in the next 5 years will mimic electric vehicle sales in Norway, Netherlands, France, and China, as you can see in this table. In the last scenario, 10% of vehicles are assumed to be electric vehicles as targeted by the state of Qatar, and it will be around 150,000 electric vehicles. Here you can see the vehicle types, charging rates used in the simulation model. We included both SUV and sedan type vehicles and different charging capacities, both slow and fast charging. I mean the level 2 and level 3 DC fast charging in the simulation model. You can see on the left hand side, only the case for Norway is presented for a 5-year demand. We selected Norway because it is the highest penetration rate. As shown in this figure, high demand occurs at night due to the charging of SUVs and reduced in the morning, because we assume that SUVs will be charged at home during the night. On the other hand, you can see during the morning time, demand is lower. This case is acceptable for the grid operator as the peak system demand occurs in the afternoon during summer months and plenty of capacity is available in winter months. In this figure on the right hand side, the worst case scenario is simulated, and we assume that 10% of the vehicles to be electric vehicles, and as I told you, it is around 150,000 vehicles. And all vehicles start charging at 2 p.m. on the peak day. And as I told you, this is the worst case scenario. In this case, the aggregate EV load, you can see, exceeds the 8.5 gigawatt generation limit and increases the peak demand by around 20%, which is not desirable by the grid operator. And it's clear that if everyone simultaneously charge their cars in the morning or evening, electricity network can become stressed. The timing of charging is therefore critical. At this point, smart charging plays critical role. So here the important question we need to answer when and where we should charge, and also of course how we can charge through the level 2 chargers or through the level 3 chargers. Now we may find the answer of this question in this slides. Till now we talked about let's say the negative impacts of electric vehicles on the power system. If we charge all the electric vehicles at the same time, the grid will be under stress and it will create some power quality issues. On the other hand, we can count electric vehicles as the battery bank of the future, and it can help for integration of renewables. Let me try to explain this concept on this famous curve, namely DAC curve. In this curve, there are at least 4 challenging situations illustrated by parts of this DAC curve. Lower belly, belly of the duck, neck of the duck, and also the head of the duck. I don't want to talk all. I will focus only the belly of the duck here. And you know the strong midday sun generates enormous amounts of solar power, and this coupled with a limited ability turn off other large generators preparing for afternoon peaks. And this could create a midday surplus of power. For example, you can see here there will be over-generation risk. A promising approach during these times would be to further increase electric load to better match solar availability. So why we are not going to use electric vehicle to charge during this time? I mean, while the DAC is quaking, we can charge the electric vehicle to reduce the overgeneration risk. So also using batteries to fill in the belly of the DAC, also we can flatten the profile. Also at other times, for example, the batteries can provide power to satisfy the loads. In other words, for example, battery can help with the head, neck, and also lower belly. You may already hear that recognizing the value of storage to meet new goals, California recently established a mandate to install 1.3 gigawatt of energy storage by 2024. To sum up, energy storage systems help for the integration of the renewables into the smart grid. So why we don't use electric vehicles as an energy storage unit? As you can see here, currently we have around 6 million electric vehicle cars on the road, and expectation is around 150 million in 2030, according to Paris Agreement alignment scenario, as you can see here. But the important question, how we can use electric vehicles as an energy storage system? How can we use electric vehicles as an energy storage system to help the utility grid? Of course, there are ways to do this, although the implementations are not easy. Let's talk about a little bit smart charging. Smart charging means adapting the charging cycle of electric vehicles to both the conditions of the power system and the needs of the vehicle's users. And smart charging comes not in a unique approach, but it can be implemented in different ways, from basic approach to more advanced approach, as you can see here. Basic approach on the top and going to bottom of the discharge, the most advanced smart charging approach. I'm not going to discuss all of this approach here. Mainly, there are two smart charging options, unidirectional and bidirectional smart charging, as you can see here. And I would like explain a little bit more how bidirectional smart charging works. Of course, it is important that the market structures and regulations are in place to enable bidirectional charging. Here we can see how electric vehicles can provide ancillary service to power system. For example, this, for example, the stored energy in electric vehicle can be used for peak shaving or as a backup source. As we just mentioned one slide before, uh, here, this is the, let's say, solar energy we are generating through the PV system. And during this time, for example, we can charge the electric vehicle, and during the, let's say, peak demand, we can shave. We can use electric vehicle for peak shaving. Here, for example, another we can use as ancillary services. Let's assume that at this time there is a fault in the grid, so there will be grid failure. So we can enable our batteries from the vehicle to transfer energy to grids. So we can use the energy in our vehicle's battery to support the grid during this time. Of course, it may not be too long, but at least it can support the grid. And you can see this can help to displace more expensive generation and lower electricity prices as well. Here, different studies and different scenarios you can see here. If according to IRENA study, you can see they assume 50% penetration. And if you use uncontrolled charging, it will increase 9% peak load. And on the other hand, if you use the smart charging, increase in peak load only 5%. Okay, and there will be no any let's say solar curtailment, 0%. And for the, let's say, RMI, if the penetration level is 33, you can see the peak will be around, increasing the peak will be around 11%. On the other hand, if you use vehicle to grid technology only, the increase only will be 1.3%. And more information can be found in the studies. And it is clear that smart charging help to limit the increase in the peak load. Here I would like to present one of our studies we conducted in Kiri. In this study, we present the grid-type PV system with an integrated electric vehicle battery and its power flow control strategy. And the optimal method studied in the study is to coordinate electric vehicle battery and PV power to improve the power system performance. The system is modeled and simulated in PSCAT environment. And here, for example, this is case one study, and it shows the simulation results when there is no load in the system. It can be seen that the generated PV power tracks the maximum power point, and the system injects the whole PV power to the main grid in this mode of operation. Of course, we neglect the losses in the power converters and the distribution line. In the case study here, it shows the simulation results of mode 2 operation. It means that there are AC loads. We connect the AC loads to the system, and also electric vehicle battery connect to the system. I mean, it is in the charging mode. The initial load connected to the system is 50 kilowatts, and the initial state of the charge of the battery is 75% for the simulation study. And it is clear that the utility grid is used as the primary power source when there is no any PV generation, as you can see here during the night. The system used the utility grid as a primary source. On the other hand, PV power is used as the primary source, and the load demand from the main grid decreased during the period, this period. For example, when PV start to generate power, you can see here we are decreasing the power demand from the grid side. Even at some point, we are injecting power to the grids. And for example, when we have excess energy, you can see here, we are charging the battery. First of all, we are only supplying the load, but when we have the excess energy from the, let's say, PV, the system sends signals to charger, and the charger trying to inject power to the electric vehicle's battery. And you can see the change of the state of the charge. It started from 75% and it's increasing. And here the simulation results of case 3 are shown in this results in this figure. In this operation mode, the electric vehicle battery operates in discharge mode. It means that we are enabling vehicle to grid functionality, and it supports the main grid. The initial load connected the system, in this case 100 kilowatt, and the initial state of the charge of the EV battery is the same, 75% for the simulation study. And there is also minimum allowable EV battery state of the charge. We are calling it reserved value is set to 70%. It can be seen that EV battery supports the main grid to cover the load demand till the state of charge reaches 70%. We are reserving this state of charge because maybe the driver want to go someplace, so we don't want to totally discharge the battery. So, summary of key messages. Of course, the electric vehicle chargers in extreme hot climates need to be designed for high efficiency, thus reducing cooling needs and improving reliability. It is very important to design such kind of, let's say, infrastructure according to the environment. And also smart charging is particularly important in extreme hot climates due to the substantial cooling load from buildings. This together with uncontrolled EV charging may increase the peak demand stress on local grids. Therefore, market structures and regulations to enable smart chargings are key. So again, I would like to thank Qatar National Research Fund for supporting our projects. And thanks for your attention. If you have any questions, you can just send me email. I will be happy to answer as soon as early as possible. Thank you.